السلام عليكم طلاب. هاي محاضرتنا اليوم هي تكملة لموضوع الايونيك equilibrium. هي المفروض ناخذها احنا يوم الأحد بالنسبة للفيزيكال فارماسي. هذا الشابتر الايونيك equilibrium احنا أخذنا البداية مالته مقدمة and today we're going to have a quick review to what we had already said and then try to finish the equation related to that subject. In the last lecture we talked about the objectives and the theories and the acid-base equilibria, and today we will try to talk about the calculation of the pH and acidity constants, and finally the effect of ionic strength. We start by asking questions regarding why as a pharmacy student you need to study ionic equilibria, and we say that every pharmacy student need to know how to define acid and base according to different theories, what is the Sorensen pH scale, how we can understand different terminology that we're going to use it even in different subjects like Ampholytes, Ampholytes, and etc. Ionization of polyprotic electrolyte and how we can calculate the pH and the pKa. The first theory was Arrhenius theory, and we said that Arrhenius defined acids as any substances that have the ability to liberate hydrogen ions, and the base as any substances that can supply hydroxyl ion. But we said this method or this theory failed to explain the representation of ionization in the aqueous and non-aqueous system. So mainly Arrhenius studied the ionization by these definitions on the aqueous solution. It didn't explain what happened in the non-aqueous system. That's why we have the other two theories. The other theory is the Bronsted-Lowry theory, and we say the Bronsted and Lowry defining acid as any substances, charged or uncharged, that have the ability to donate proton, while the base, any substance charged or uncharged, that have the ability to accept proton from an acid. And according to this definition, we have any basic material when react with acidic material, we have the base converted into conjugate acids and the acid converted to conjugate base. Here we talk about how the strength of an acid or base affected by the solvent, and we talk about what we call it the basic strength of the solvent. This is what is the meaning of this. We mainly focus on the material, and we said it is acid, strong acid, when it's have the ability to give the proton, and at the same time we have a base that have the ability to accept proton to very high degree, and that's why we call the hydrochloric acid in water as strong acid. But in the glacial acetic acid is weak acid. Why? Because the water have high ability to accept the proton from the HCl, while the glacial acetic acid have low ability to accept proton from the HCl. According to Bronsted and Lowry theory, we can classify solvent into four major types. The first one is the protophilic or the basic solvent. Those solvents have the ability to accept proton, and example for that acetone, ether, liquid ammonia. And the other type is the protogenic. From the name, it's protogenic. That means it's going to generate proton. It's proton donating solvent. Example, the liquid hydrochloric acid and liquid hydrofluoric acid. And we have another which is amphiprotic, which are the solvents have act as both proton acceptor and proton donors depending on the nature of the substance that we adding to it. And we have aprotic solvent, which is the solvents, for example, hydrocarbons, that they have the ability to accept neither to donate a proton. So they can't accept, they can't donate a proton. And they are very useful to study reaction where the acid and base is free from the solvent effect. When we need to study the properties of the compound away from the solvent effect, we need to use an aprotic solvent. And then we define the protolytic reaction, and we say the protolytic reaction, it is any type of acid-base reaction that is involving the transfer of a proton from the acid into the base. And we have different types, for example, neutralization, hydrolysis, and displacement reaction. All of those are including in the example table that you have here. And the final theory we want to talk about was the Lewis electronic theory. In the Lewis electronic theory, Lewis tried to explain the behavior of some compounds that acting as acid or base and they don't have a proton to share or to donate. And for example, for that, if we have this example here, this is ammonia, and in the ammonia we know it's have the ability to accept a proton, so according to Bronsted it acts as a base. But when we try to react the trifluoroboron with the ammonia, what we have here in the trifluoroboron, it's a compound that does not have any proton to share. How it's going to act as an acid? So Lewis changing the definition of acid into this one. According to the Lewis, acid is any molecule or ion that have the ability to accept an electron pair because it have an unshared orbital. While the base is any substances that have the ability to provide unshared electron by which the base coordinate with an acid. And this is the example for the Lewis electronic theory. Here we're going to talk about the Sorensen pH scale. Sorensen put a scale from 0 to 14 to define the acidity and the basicity. And he put a neutral value that is equal to 7. This is a neutral value at the room temperature. At different temperature, the neutral value is going to be different. For example, when the pH at 0 centigrade, the neutral value is 7.47, and at 100 centigrade, the neutral value would be 6.15. Now, so what's about this scale? The scale is ranging from 0 to 7, presenting the acidity, and when we approach the 0, we have higher acidic, and from 7 to 14, it represents the basicity. When we approach the 14, we having the high basicity. And here we talk about the derivatization for the equation to calculate the H for the weak acids compounds, and as we said previously, for the calculation of the OH for a basic compounds, it's homework. All of you need to try to study that at home. And for example, this is mean ionic. What's the meaning? I will try to review it quickly. What is the meaning of ionic equilibria? Equilibria, it's mean equilibrium, and we arrived that when we have the rate of forward reaction is equal to rate of backward reaction. So at equilibrium, we can have this equation. Substitution the equation with the constant of the water concentration that is equal to 55.3. We finally arrive to this equation that is the Ka, which is the acidity dissociation constant, is equal to the concentration of the both ions that dissociate ions, which is the H3O plus and multiplied by the acetate ion concentration and divided by the original concentration of the acid. Why it is only original concentration? Because the x, which is representing the dissociation constant, is a small value, can be neglected compared to the original concentration. And here we explain the correlation between the Ka and the Kb depending on the Kw, and we called it the Kw as autoprotolysis constant or ion product of water. And we have example here when we have an ammonia with a pKa of 1.74 multiplied 10 to minus 5 at 25 centigrade, calculate the Ka. So simply dividing the 10 minus 14 to the value of the Kb, we will have the Ka. So try to use the equation that we learned previously to calculate and answer this example. Here we're going to talk about the ionization of polyprotic electrolytes. When we have an acid that have the ability to give only one proton, single proton, it's can called monoprotic electrolyte. But sometimes, especially in the medicines, we have so many drugs that's having multi-protons, so they have more than one proton. What we call them? We call them a polyprotics. That means they are the compounds that have the ability to donate two or more protons. One of the major examples for this is the H3PO4, the phosphoric acids. And here we're going to explain how this compound is going to dissociate. So here we have the H3PO4 that's going to dissociate firstly to give the first proton and give H2PO4 minus 2, and this H2PO4 going to dissociate and the HPO4 going to dissociate by itself. But we have the Ka of different value. The first Ka is 10 minus 3, the second one 10 minus 8, and the third one 10 minus 13. Why we have different value for the Ka? Firstly, because the In the beginning, we need to take the hydrogen ion, the proton, from the neutral H3PO4, but in the next step, the negative charge of the HPO4-2, it makes more difficult for water to remove the proton from the phosphate ion, and this is reflected by the small value of the Ka. And so the phosphoric acid is weakened in the third stage of ionization and solution of the acid containing practically no PO4-2. In reverse, the PO4-2, it can behaving as a base, and each species formed by the ionization of polyprotic acid can also act as a base. And here the PO4 have the higher Kb value from the others. As we said, PO4-3 would be having higher tendency to to accept the proton and converting to HPO4-2 and so on. So from the Kb 10-2 to 10-7 and finally 10-12. And we talk about this protolytic reactions and the effect of the thermodynamics and how the Ka can be correlated with the delta H of the equations, and you need to review that to have better view of the subject. The final part of the last lecture was talking about the ampholytes, and the ampholyte we said is the substances that have the ability to donate and accept proton. When they have the ability to accept, and the one of the major examples of compounds that have the ability to accept and donate protons are amino acids. And the amino acids have the ability to react with water. For example, one time we having a neutralization to the carboxylic part, and the other time we having ionization to the amine part. When both of the groups are ionized on the same molecule, we have a special term for this molecule. This is called the Zwitter ion. So what is the Zwitter ion? In the Zwitter ion, we have two parts of the groups, two functional groups on the same substance that ionize at the same time. And this is Zwitter ion have highly applications in pharmacy, especially in the protein. As we know, the protein consisting mainly from amino acids. That's why it's having two parts like carboxylic parts and amine parts. When we have both of them ionized in the same time, we have what is called the Zwitter ion. As we said, the Zwitter ion is important, and one of the important application of the Zwitter ion is the isoelectric point. The isoelectric point of any compound, it's the pH at which the Zwitter ion concentration is at maximum. And it has been used for determination the type of proteins, type of amino acids, and so on. And we have here some homework examples about the application of the isoelectronic points. For it's in the term of blanks. The molecules have blank solubility at its isoelectric points. So when the pH is equal to isoelectronic points, what's happened to the solubility of the molecule? What is the net charge of the molecule at its isoelectric points? And what is the charge of the molecule at pH above isoelectric point and below isoelectric points? Okay, now we're going to study how we calculate the concentration of the hydrogen ion concentration, from different electrolytic solution. First, if we have solution containing strong acid, so when we have strong acid, for example, hydrochloric acid, it's going to dissociate completely. So if we have 0.1 normal of HCl, it's going to give us 0.1 normal of the hydrogen ion concentration. So the strong acid concentration of H is equal to the initial concentration of the acid. While for the solution containing only weak acids, we can use the equation that we derivatized in the beginning of the lectures. So we have the hydrogen ion concentration equal to Ka multiplied by Ca, taking the square root. So here we have example to calculate the pH of salicylic acid. So salicylic acid, it's an weak acid. It's asking about the pH when we have the concentration of 0.01 molar. So this is the Ca. And we're having the Ka for the salicylic acid is equal to this value. So simply the H, we can calculate it from the equation, the Ka multiplied by the Ca. So we have the concentration of H minus logarithm to the H, we will have the pH. Here we have another example for solution containing a weak acid, and how we calculate the pH of that solutions. For it's calculate the pH of solution containing ephedrine sulfate. The molecular weight is this value. The Kb for the ephedrine base is this value. It's important here to notice that the ephedrine sulfate, it's going to dissociate to give completely two ions of the ephedrine cation, which is act as an acid. So we have one from the ephedrine sulfate going to give us two from the cation. So we need to multiply the original concentration of ephedrine sulfate to get the concentration of acid. And then we need to calculate the Ka from the Kb that we're having in the questions. And finally, we can get the H by applying the concentration, the equation that we talked about previously. And finally, we converted the H concentration into the pH. Okay, now we're going to talk another scenario when we have solution containing only a weak base. And in the question you have asked about the calculation of the pH. There are two ways to calculate that. First, either you calculate OH from the equations that you have to derivatize it as we said previously, which is equal to Kb multiplied by the concentration of the base to the square root, or we can use directly from the Ka by using this equation, which is H3O plus concentration, the hydrogen and concentration, equal to the square root of Ka multiplied by Kw divided by the Cb. And here we have example for the solution of cocaine base. So from the name, it's cocaine base, and we having the concentration of the base, and you have the basicity constant, which is Kb, and then we can calculate Ka. I think it's a direct application here. Another scenario here when you have a single conjugate acid-base pair. What do we mean by single conjugate acid-base pair? In this one, for example, if we take acetic acid, so it is the acid. What is its conjugated base? It's the acetate ion. From where we can get acetate ion? For example, from sodium acetate. So if we take this example, what is the pH of solution containing acetic acid 0.3 molar and sodium acetate 0.05 molar? How we can calculate the pH of such solution? The pH of such solution can be calculated from this equation. The H plus is equal to Ka multiplied by the C of the acid, concentration of the acetic acid, divided by the concentration of the base, which is the sodium acetate. And here we have the H3O. Note this equation, we are going to use it later on to calculate the equation for the buffer, Henderson-Hasselbalch equation. The equation that used to buffer, we can convert this into that equation, which is equal to pH equal to pKa plus logarithm of the concentration of the salt divided by the concentration of an acid. And here this direct application to the example. Here we have the same case, but we have ephedrine as a base with ephedrine hydrochlorides as its conjugated acid, and we can apply the same equation to calculate the pH. Okay, now what will happen if we have solution containing two weak acids? For example, we have acetic acid, which is a weak acid, and a formic acid, which is also a weak acid. How we can calculate the pH of such solution? It's directly by applying this equation, K of the first acid multiplied by its concentration plus the K for the second acid multiplied by its concentration, and the whole value we can take the square root, and then we have the H value, converted it through to the pH by using the equation minus logarithm H, and that's it. Now if we have a solution of a salt of weak acid and a weak base. For example, the salt of ammonium acetate. So what is ammonium acetate? It's a salt composed from acetic acid, which is weak acid, and ammonia, which is a weak base. When we have these react together, we will have ammonium acetate. So if we have ammonium acetate with a concentration of 0.01 molar solution, what is the pH of such solution? Here we need to having this equation, which is the H plus is equal to K1 multiplied by the K2 to the square root. So what is the K1? The K1 is the dissociation constant of the acid part. What is the K2? It's also the dissociation constant of the conjugate acid to the base part of the molecule. What we mean by that? For example, we're taking the ammonium acetate, so the K1 is the Ka of the acetic acid, and the K2 is the Ka of the conjugated ammonium. That's we calculated it from the 10 minus 14 divided by the Kb of the ammonia, and we have the rest of the answer as you can see here. Here we have a situation when we have weak acid added to a weak base. So what we can have here, when you add weak acid to a weak base in the same concentration, you're going to have salt composing from weak acid and weak concentration. So it's similar to the previous situation. You use this equation, for example, H3O plus equal to the K1 multiplied by K2 to the square root, and K1 is the dissociation constant of the acid part, and the K2 is dissociation constant for the conjugate acid for the base part of the equation. And here you have a simple application to that example. Now we're going to talk about the ionic strength. If we take any substances, for example, the NaCl, and we dissolve it in water, what's going to happen? First, the Na, which has a positive charge, is going to separate it from the chloride, which has the negative charge. Around the Na, the positive, there would be accumulation of the partially negative part of the H2O, which is the oxygen. It's going to take partially negative and accumulate surrounding the Na. And the H, which is the partially positive part, going to accumulate surrounding the chloride part, negative. And this is forming what is called ionic atmosphere. It is like a shield surrounding each one of the cation and the anion. The best descriptor for that shield is called the ionic strength. So the ionic strength was first introduced by Lewis and Randall in 1921 while describing the activity coefficient of strong electrolyte. So the ionic strength of a solution is a measure of the concentrations of ions in that solution. And here when we have a more charged molecule, it would be counted more to the ionic strength because it has stronger electrostatic interaction with other ions. For example, if we're talking about Na2SO4 minus, so SO4 minus Na, it would be only one positive, while the SO4 is double negative, so it has stronger electronic cloud rather than that of the Na, and so on. Okay, how we can calculate the ionic strength? The ionic strength, or the mu, can be calculated using this equation, is equal to half divided by the summation of the concentration of each ion multiplied by its charge to the square. So if we example taking 0.1 normal of NaCl, how we can calculate the ionic strength of this molecule? First, we need to draw the dissociation of NaCl. Dissociation of NaCl is giving us Na plus chloride minus. And when we have original concentration 0.01, so the Na concentration would be 0.01 and the chloride concentration 0.01. And here we apply the equation mu equal half multiplied by the concentration of the sodium, which is 0.01. The charge of the sodium is 1 square plus the concentration of chloride 0.01. The charge of the chloride minus 1 square. So the overall would be equal 0.01 molar. So this is the ionic strength of 0.01 molar NaCl. But if we take 0.01 molar Na2SO4, what would be the ionic strength? Okay, first we have the dissociation constant of Na, the dissociation equation of Na2SO4 that gives us 2Na plus 1SO4. The 2Na would be the concentration of Na equal 0.02, and the SO4, the concentration would be 0.01. And when we apply the concentration half, multiply the concentration of Na, what is the concentration of Na? 0.02 multiplied by 1 square. Then the concentration of SO4, which is 0.01, multiplied by the charge. What is the charge? Is minus 2 to the square. And the overall is equal to 0.03 molar. That's why when we have a similar concentration of NaCl with Na2SO4, we will not expect to have a similar behavior of electrolyte in this solution. Why? Because the ionic strength of NaCl is equal 0.01, while the ionic strength of Na2SO4 is equal 0.03. So now, what is the effect of ionic strength on acidity constant? Actually, when we talking previous about the acidity constant, we usually use the multiplied concentration divided by the concentration of the original acids. But it is not the real pictures, because the effect of ionic strength, when we having a dilute concentration, that is true. But when we have a higher concentration in solution rather than water, for example, in solution of NaCl, in solution of Na2SO4, what would be happening in the dissociation constant? Here we need to, instead of using the concentration, we need to use the thermodynamic representation of the concentration, which is here called alpha. So the alpha is the thermodynamic effect of the H plus the thermodynamic effect of the conjugated base and divided by the thermodynamic effect of the conjugated acid. And how we can get this thermodynamic from the ionic strength. For if we have a monotropic molecule and we need to calculate the pKa of that molecule at different ionic strength, we can apply this equation. So pK prime, instead of pK, we're now using pK prime. That's equal to pK plus 0.5 to 2 multiplied by the charge minus 1 to the mu under the square root, and here we have 1 plus mu for the square root. So this is for monotropic molecule. If we need to calculate any of the previous equations, all of the equation we're talking about, and we need to calculate it by effect of ionic strength, the first step to calculate that, we need to convert all pK value into pK prime using this equation, and then we apply the equation as usual. Now, what will happen if we have a Zwitter ion? So with the Zwitter ion, as we said previously, we have two parts of ionization. So we can have pKa1 and pKa2. By applying this equation, we can calculate the effect of pK prime for both of them. And here in this equation, we have what is called the salting in constant, which is a constant for the amino acid in water, and that's equal 0.32. So applying this equation, converting the pK into pK prime, and solve the problem appropriately. Here is the example to show the effect of the ionic strength. Now it's asking about calculating the pH of solution of acetic acid. So acetic acid, we usually using the first equation to calculating the H and then calculating the pH. But here it's asking the concentration of acetic acid in KCl. So when we add the KCl, can affecting the ionic strength, and we could have a different Ka value. So the first step, converting the pK into pKa prime, and then calculated as we showed previously. And here we have another example for the effect of ionic strength on the amino acid glycine. Glycine is one type of the amino acid that's having two pKa value, one of the acid part and the other one for the basic part. When we try to calculate at different ionic strength, first converting the pKa into pK prime using the applied equation, and finally solve the problem as the usual equations. And thank you very much for your attention. This is the end of this chapter. Please feel free to contact me if you have any notes or questions regarding to these lectures.